So stop.
Yeah, so please stop sharing. Yeah, that's right. Thank you very much. Thank you very much for your talk. Yeah, and Pawan,
Thank you, sir.
if you could start sharing and
Yes, sir.
start your talk. We can hear you. I'll let you know if we can't hear you. I'll let you know.
Okay, so everything is okay.
Everything's perfect. Yeah.
Yeah. Good evening, everyone. Myself, Pawan Negi from IIT Kharagpur. Today, I will be presenting on the wave scattering by an array of submerged trapezoidal breakwater. We will here develop an analytical solution for the same. Okay, so moving forward, the outlines of my presentation will be as follows. First, I'll give the objectives of the present problem and then the relevant motivation. Then some relevant literature review, and after that I'll dive into the mathematical formulation, giving the physical assumptions, explaining the schematic diagram and the governing differential equations. Then some numerical results and discussion, and after that some conclusion and future scope for the present problem. So as we know, the breakwaters are used to create a tranquillity zone for various humanitarian activities. Like here we can show see a breakwater creating a tranquility zone for the parking of the ship and other humanitarian activities. And here's a picture of the Palm Island in Dubai, where we have a lot of entertainment facilities over this region. And then in the France, we have a porous breakwater, basically a circular porous breakwater. Nowadays, we are listening towards the V-shaped and the arc-shaped breakwaters as well, deployed in the ocean. So with this motivation, we are going to study the submerged breakwater, and that too in the trapezoidal shape. So the objective of the present study is to study the interaction of gravity waves with the narrow submerged trapezoidal breakwater. The simple physical problem is considered in 2D Cartesian coordinate systems, and then we solve the Yee equation analytically over the basically what we have the front and the back slope of the trapezoidal. And here what we are extra doing is we are choosing the bed profile such that the dispersion relation has an exact solution. What I mean by exact solution, I will discuss in the further slides. And then for the method of solution for like an array of trapezoidal, we use the transfer matrix method. And then the present method will be validated against the mild slope approximation used to counter this problem. Earlier, the researchers have used the mild slope approximation to counter this problem. So coming to the literature review, although many literature is available for the gravity wave interaction with the trapezoidal breakwater, but here I present which is relevant to our present work. Liu et al. Have derived the analytical solution to the modified mild slope equation for wave propagation over the piecewise smooth topography, and then J.N. Hunt has given the direct solution to the wave dispersion relation, obviously in some special cases of shallow and deep water. And then Liu et al. Have developed the analytical solution for the combined reflection and diffraction based on the mild slope approximation. Also, the study has been extended to analyze the truncated paraboidal breakwater, is the breakwater in the paraboloid shape. And then Zai and Liu have analytically studied the linear wave transformation in a breakwater, trapezoidal breakwaters and trenches using the modified mild slope approximation. And then Ye have derived the known Ye equation for the water wave propagation over the topological bottom. He has taken mostly the rectangular trenches to study this problem. Okay, now coming to the schematic diagram, here I show this schematic picture of the array of trapezoidal breakwater. Here we have two regions. This is the front slope and the back slope, and then this is the flat region of the trapezoid. Now we assume that the front slope and the back slope basically extend up to the length of W1 and W2, whilst this horizontal trench extends up to the WT. However, the gap between the two trapezoid is denoted by WG. And so in this region, we have separate regions, basically the front slope, back slope, and this gap region, and this flat portion over the trench. Here we have assumed the fluid to be inviscid and incompressible, and the flow is irrotational with simple harmonic in time with frequency omega. Okay, so, and yeah, here the water depths are considered to be H0 from the incident side and H2 on the at the end of the last breakwater. Mostly for the computational purpose, now I have fixed H0 equals to H2, but for the unsymmetrical geometry, we can consider H0 not equals to H2, and the problem still works fine. Okay, now, so here what we have done, we have chosen the bottom bed profile to be of such fashion where over the flat seabed, the water depth is H0, H1, and H2. But now coming to the front slope and the back slope region, we have this kind of basically this bottom bed. Now, specifically why this kind of bottom bed have been chosen, because then the dispersion relation, basically the surface gravity dispersion relation, omega square equals to gk tan hyperbolic kh, will lead to a exact solution if we consider this type of bottom bed. And this can be proved easily also using the function identity of tan hyperbolic functions that I'll discuss in the later slide. And here mu is just a constant that is given by omega square by g. Just and our L1 and L2 are functions defined in this way, such that these functions for all x remain bounded between 0 to 1. Okay. So now, again, if we have chosen that bar symmetry of the present form, then there are these constants, basically A0, A0, and A2 can be determined by using this formula, and it depends upon the wave frequency. So we can say, depending upon our incident wave frequency, the bottom bar symmetry will change a little bit. Now, as I have said that um, basically following the approach of Xi, we can say that the dispersion relation will have an exact solution if we choose a particular type of bathymetry that I have shown beforehand, and the wave number will be explicitly given by this form, mu by just Lx. So basically you can put the value of x equals to x naught or something, and then you can get the correspondingly wave number. And this can be proved using the function identity of tan hyperbolic x, because the tan hyperbolic function can be written down as log of root over of 1 plus x upon 1 minus x, and the theorem will be proved straight away. Okay, so we don't have to use the original dispersion relation like omega square equals to gk tan hyperbolic kh. Either you calculate the root from there, or from simple this formula, the roots will match. I have checked that also. And then, okay, now from the work of VA, we have directly taken upon the equation which satisfies the surface elevation eta over the any undulated bottom bed, and the equation reads like this. However, when we have a constant seabed like here where H0 and H1, and then here we have H2, this A equation will transform into the known Helmholtz equation, and for that we can write the solution of this way in each subdomain. Here my A3j, A4j, A7j, and A8j are simply the constant unknown complex constants, which will be determined using the interface condition at these trapezoidal breakwaters. And actually these represents the to and fro motion of the wave in each of the regions. And here my AR and AT are the complex wave amplitude associated with the reflected and transmitted waves. Now, although we have find the solution over each of the constant bottom bed, but coming to the front and back slope, this A equation we can open up and substitute the value of we can substitute the value of K from this formula and get a new equation, and then using some algebraic manipulations and mapping, we can get the solution on the front and the back slope in the form of the Bessel functions of zeroth order of first and second kind. Basically, the A equation will transform into a Bessel equation of zeroth order. And in each slope region, we can write this solution this way. Now here we have got this tau x of this way, and the epsilon x is a function of this way. So what we do now, like over here the picture, now we apply the continuity of eta and the slope of eta at each of these interface, what I have shown by dotted lines, and then we can have a system of equations which can be written down as this way, where I have 1, 2, 3, 4, 5, and 6 system of equation, and then they can be clubbed together to get a transfer matrix method, and then we can have AR and ET of this way. And here I like to point out that these matrices in general are not commutative, so we cannot change the order of these matrices. And from here I can easily compute my reflection coefficient, which is modulus of AR, and my transmission coefficient, which is a modulus of AT. Now coming to the validation of the present problem, the problem is validated with that of xi and u. And here what we have done is, in their method, they have used the modified mild slope approximation to deal with the same problem of the trapezoidal breakwater, but that was a single breakwater. Now here we have plotted the again result with the corresponding value, and the values are fixed to be W1, W2 as 2 meters, and the trench width and the gap width is 28 meters, and the water depths are like this. So we see there is a perfect match with that the result of xi and u. So we know that the theorem that we have established for the exact value of the wave number is correct. Now here the reflection coefficients are plotted for in the first case for odd number of trenches, and for the second case for the even number of trenches. Well, obviously when n is greater than 1, is basically greater than 1 for 2, 3, and 4 trenches, we can see the subharmonic peaks. The subharmonic peaks occur in the system, whilst for n equals to 1, no subharmonic peaks were occurring. There was only a oscillatory decreasing pattern of the reflection coefficients. Moreover, as the number of trenches increases, the number of subharmonic peaks will also increase. Now, here the again reflection coefficient was plotted for versus the W1. W1 is the length of the front slope. So again, we can see for n equals to 1, no subharmonic, although it is oscillatory, but no subharmonic peaks will occur. But when n is greater than 2, then we have n minus 2 subharmonic occurring for any given n. Like for n equals to 3, I have a single subharmonic. Right? For n equals to 5, I have 3 harmonics in between the 3 subharmonics in between the 2 harmonics. And the same result will be carried on for the even number of trenches. Basically, for n minus 2 formula works for n equals to 2 trenches, because we don't have any zero subharmonic, only the harmonic peaks are there. Now here again, the same result is plotted, but for the various values of Wg, basically the gap width. So when n equals to 1, there is no role of the gap width, so the reflection coefficient is constant. However, when we increase the number of trenches for 2, 3, and 4, and 5, 6, we can see again we have the number of subharmonics, which can be given by the formula n minus 2 for each of the cases. Okay, so here I have plotted the elevation for single trench, double trench, triple trench, and 4 breakwaters, 4 breakwaters. And we can see that the reflection coefficient is basically the reflected wave amplitude is increasing as the number of trenches we increase, and which is obvious also because a 4 breakwater will provide a better tranquillity zone in the transmitted region as compared to the single breakwater. And yeah. So with this, I have done till this now, and now we are moving towards the fractional gravity wave and the membrane covered surface to derive the explicit expression of this dispersion relation. In the case of fractional gravity wave, can we get an explicit formula like we have got in the surface gravity wave? So we are now working towards that, and it will be extended to the case of fractional gravity wave and also to the membrane covered surface. Also, these these breakwaters, a little manipulation in the values can give us breakwaters also correspondingly. Those results I have not shown because they are similar in nature, only the Bragg resonance peak has shifted towards the right only. So these are the references for the today's talk, and thank you for your attention. And if any questions, I will be
Yeah,
ready to
thank you very
answer
much,
them.
Pawan. Really interesting. And there's plenty of time for questions as well.
Yep.
I'll just, if no one else is going to ask a question, I'll just ask you. So, Pawan, I'm just trying to follow this talk. So it's shallow water, right?
Yeah.
And there's no, it's just shallow water.
Yeah.
It's no plate, nothing like that. And then,
No, it's the surface gravity waves. Yeah.
yeah. And
Actually, the
then,
main idea. Yeah.
and then these trapezoidal trenches, they're not straight lines. They have this weird shape. Is that right?
Yeah. They are not straight lines. I'll
So
show.
they're
They are
given
not
by
straight
this,
lines. They are basically they are not even the linear slopes. Also, they are somewhat a square root function. But
and that when
like
you do
yeah,
that, then you
yeah,
get an exact solution for the dispersion equation for
yeah,
shallow water, which is some
yeah,
Bessel function, right?
yeah. You get basically you can get the dispersion relation of this fashion. So whatever your Lx, basically the constraint of this problem is that Lx should be bounded between 0 to 1 for all x. If you can find out any function or any shape, it will work for paraboloidal shoal also, provided the Lx should be bounded between 0 and 1. If this is bounded between 0 and 1, you can approximately exactly write the wave number in this way, and it will give you the same result as for the uh, normal dispersion relation. So that is one case. And then you can, what is the advantage of this method? Then you can take any bathymetry. You don't have to go with a rectangular or some regular shape. You can go with any bathymetry provided your Lx should be bounded between 0 to 1. It's just that constraint. So there can be like, if we can even construct linear slope, whatever the literature is showing, we can construct linear slope for this. We can construct paraboloid. We can construct even circular.
But then what's the
Yeah,
function that's a solution in that region? Is it this Bessel function or for all these different
yeah, okay. So now we have this A equation. Okay.
Yeah.
So over when we put the wave number mu by Lx here and we solve this equation, we will get the zeroth order Bessel equation. And for that, the solution is written like this: J naught and Y naught.
Okay, wow. Okay.
How,
So,
however, this
and
YE
this is
equation
all
for
from sorry, this is all
Hmm.
from this paper by Yay, is that right?
Yeah. This kind, yeah, and basically one more reference, this JJ. Two paper I have basically the basis of this work.
But how do you think this will extend to the case of the plate covered surface? I mean, it's
Yeah,
not a given to me that that will happen.
actually, what we are currently, my idea is like I have said that the Lx is a bounded function between 0 to 1. Suppose it is bounded between 1 to infinity, then I can write it as 1 by L1. So Malab, I have to check the dispersion relation and then I can say anything. But my idea is that I have strictly speaking that it should be bounded between 0 to 1. But if it goes between 1 to infinity, bounded between 1 to infinity, so we can like write the converse of this, like 1 by L1, and then here we can write 1 by L1, 1 by L1. So that theorem still holds for the other bathymetry also. So we can get a large area of bathymetry. And actually, I'm going stepwise. I will first see the Lambent cover surface. If that dispersion relation can be approximated similarly in the case of surface gravity wave, then I'll jump to the textual gravity wave.
Yeah.
So that is still under progress. So that we are.
Yeah.
Uh,
Is there any other questions?
yeah, but Pawan in shallow water is not tan hyperbolic cage. It is only
Yeah,
cage.
yeah, That I know. Actually, I have approximated the finite water depth only because shallow water mein, so it's obviously
Okay, so
basically
there
no.
are little more complexities there.
Yeah, and basically the idea is that you can take any bathymetry depending upon the Lx. It is
No,
not
no,
like you have to take only rectangular. That is there.
this is fine. You can take any means compared to boundary element analytical solution, but that part also
Yeah,
you have to consider. It's not tan hyperbolic.
Bolic term, yeah.
All right. Yuri, did you have a question?
Yeah, I was going to give just a comment.
Yes.
The problem for one trench was solved in one of my papers. I can send you a copy of this paper, Pawan.
Okay.
And it was shown also that there are some other profiles with exact solution. In particular, if the slope is a hyperbolic function, it can be also obtained an exact solution. And moreover, if the profile is described by tangent hyperbolic, again, exact solution can be obtained. Okay, so yeah, I will send you a paper. You will have a look.
Yes,
So,
definitely.
and you can also compare a solution for one not
Trench,
range but hump actually. It's not a trench. Okay.
Okay.
Yeah, with your solution.
Well,
Yeah.
these could be humps as well as trenches, couldn't they? But I mean, where's
Yeah,
the level?
if it is only one, of course it is hump.
Yeah, correct. That's true. Good point. Only one. Yeah.
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 Yeah, interesting study.
There's nothing about this that has to go. If it went down, and it would be the same solution.
Yeah, there is also could be an interesting extension of that if you consider a periodic set of such humps and obtain a solution for the periodic topography.
Okay.
Yeah.
Yes. Yeah, that's right. And then look at path bands and all right. Is there any other questions for Pawan?
Professor Yuri, hump means do we have a straight bottom over it, or it will be like a semicircular kind of breakwater?
You mean bottom profile?
Yeah. What you are talking about hump, will it be a semicircular hump or a
No. I mean similar profiles which allows us to obtain exact solution.
Okay.
For individual one.
But going up. Yeah, a hump means it just means going up.
Okay.
Yeah. It's not a particular shape, a hump.
Okay.
Yeah. But for such particular shape, yeah, we can construct exact solution.
Okay.
And it's a bit of a colloquial term, a hump, but it is used. You know, it is used in the literature. All right, Pawan, well, you must be close to finishing your PhD, I would have thought.
Yeah, I will be submitting in December 24th, 25th, mostly.
So this is not going to be part of your thesis, is that right?
Yeah, this will be a part of my thesis actually.
I'll keep working then. Okay. Still a month to go. All right. But unless there's any questions, we do have time. But I think we'll stop there and we'll move to this last talk.